okay, you can test and reuse it without calling the compare function again. Okay, some of you will write that if S1 dot measure, okay, measure of S1 dot compared to measure of S2 is not zeros, then you return measure of S1 dot compare with measure of S2. So you call the compare function more than once, but doing the same thing. Okay, so if that function, okay, has a complexity that is not a constant, it's not an order 1 operation, and it's better for you to save the results so that later on when you need to reuse that result, you don't need to repeat the computation steps. Now when you are using the B-search function, when you are using the B-search function, you need to provide 5 parameters. Okay, the last 4 parameters are the same as the requirement of QSORT. Okay, meaning that you need to provide the starting address of the array, the size of the array, the size of every object in the array, and the compare function. Now you need to provide also an address value that is the address of the key record. So to provide this parameter, okay, one better way to do it is that you define an automatic variable of the different structure type. Okay, then you fill in, okay, the corresponding data fields of the record, okay, with the search value. Then you can call B-search by providing the address of the local variable. Now the B-search function will return to you a void pointer. So if the key is not found, then it will return the null value. Okay, if the key is found, then it will return a weighted address. Okay, that is pointing to one of the objects in the array. Before you use the returned address, you need to do a typecast. Okay, because the returned value of B-search is a void pointer, so it's a pure address without data type information. Okay, so in order for you to make use of the returned value in the subsequent computation steps, then you need to tell the compiler now how you are going to interpret the return address. Okay, what is the data type? Okay, at the given address location. Okay, so we do a typecast and then save the value in a local variable P. Now before you use that value, you need to do a test to make sure that it is a weighted address. Okay, then you will use it in other steps. Okay, so if P is a null value, then this subtraction may give you either a positive or negative value. It all depends on, okay, what is the absolute address of your array when, okay, you request the system to do the dynamic memory allocation. Okay, so we don't know, okay, what will be the exact value of this. Okay, so if P is not a weighted pointer, don't use it in other computation steps. Okay, so this is the basic part. Now coming back to today's exercise, okay, as I point out to you in the lab, that you can reference the example codes in the notes on page 3 for the delete operation. Now, in the singular linked list, every node only have one pointer that points to its successor. So if you need to modify the structure of the linked list, you need to know the predecessor of the node that you may want to delete. Okay, without knowing the predecessor of the node that you want to delete, you will not be able to modify the structure of the linked list. Now the variable head used in this example is based on the case that in the nodes we use the name head to refer to the pointer that is used to point to the first node in the linked list. Now you have to understand that the name of the variable is context dependent. So in this example we use the name head. In the tutorial, the name of the variable that points to the first node in the first list is called list A. Okay, so you need to know that when you write your program, what's the name of the variable that you will be using. Okay, don't say that you see something in the node set with the name head and then you define some variable locally with the name head and then you do a copy of exactly the same code and it won't do what you want the system to do. Okay. So when you do the study, in particular for this course, when you read the notes, you need to go through the example programs line by line and understand the meaning of each statement. Don't try to just memorize the codes, hoping that in the test or exam you just repeat some of those codes and then that will be the answer. No. Okay. So if you don't ever spend any effort trying to understand the program codes in the notes, then I would say that you won't learn anything in this course. In the past, students always say every semester, or some students always have the comment saying that the notes are difficult to read, and the notes are not helpful for the preparations of the test and exam, because if you just want to spend one day to do the revision and then go for the exam, sorry, you can't do it this way. Why it is important that you must be able to understand program codes is in the future, if you happen to be a programmer, that you write certain programs or you're working in a team, you must be able to understand programs written either by yourself or by other members in the team. Okay. If you can't understand simple program codes like this, then you will never be able to write any meaningful programs. This is some basic skills that you need to master. Now, in today's exercise, we just work on the simplest types of linked lists. Okay. In reality, very seldom we use this single linked list these days. Okay. In most of the other language, the built-in linked list is a W linked list. Okay, that every node will have two pointer variables that points to the predecessor as well as the successor. And this type of linked list is also linear in the sense that it is a one-dimensional structure. Okay. The uses of linked list in a program in general will not be for this kind of purposes. More often, linked lists are used to construct multi-dimensional data structures. Okay, one example that I'm going to show you is called an orthogonal list. Okay. Now, an orthogonal list is a two-dimensional linked list. Okay, one example application is to use this kind of 2D list structure to represent some high-dimensional sparse matrix. Okay. Now, one properties of sparse matrix is that in the matrix, okay, or the dimension of the matrix can be very, very big. Okay, maybe 10,000 by 10,000, or even 100,000 by 100,000. But the number of non-zero members in the matrix is a small percentage, maybe just 1% or less than 1%. Okay, so instead of using a full 2D array to store a small percentage of non-zero values, okay, we will use a dynamic linked structures that will only store the non-zero members. Okay, for the zero values, we don't need to store it in the data structures, because if you don't find it, then by default the value is 0. Okay. Now, here I show you the structure of the orthogonal list. Now, in the note, okay, there are 3 data fields and 2 pointers. Okay, the 3 data fields are corresponding to the value of, okay, a member in the sparse matrix and his coordinate, okay, the row and column index. Okay, then in every node we have 2 pointers. Okay, and they are called down and right. Okay, so graphically, okay, we have the 2-dimensional list structure in this organized in this way. Okay. Now, if this is the sparse matrix, okay, with 1, 2, 3, 4, 5, 6 non-zero value. Okay, then in our representation, we will put together, okay, the numbers in a row in a circular linked list with a header node, and also the members, the non-zero members, in a column. Okay, and we put it in a vertical circular linked list with a header, and then we join together, okay, the header for all the columns into a horizontal circular linked list, and the header for the rows in a vertical circular linked list. Okay. Now, when we store a data member, okay, for example, the value 59, it is corresponding to the location at the row and column index 0, 0. So we store the row index, column index for this element, value 59. Okay, so in the node we store the coordinate, okay, of the data value, and the value itself. Okay. Now, on row 0, okay, we only have one non-zero data value, 59. Okay, so that's why in that row we have a circular linked list with one data node. Okay, and the node on its left-hand side is the header node. Now, in the header node, we don't store any weighted data value, but the header will be assigned, okay, the corresponding row number. Okay, so this circular linked list corresponds to row 0, and the column index is set to -1 because it's not a weighted column index, because it's just a header for the row. Okay. Now, for the second row, we have 2 data values, 71 and 9. Okay, so in the structure, we have a circular linked list, horizontal circular linked list with 2 data nodes. The first data is at index 1, 0. Okay, row number 1, column 0. And the second data is at row number 1, column 2. Okay, and then the header node for this row will have the row value set to 1 and the column value set to -1. Now, for the first column, okay, we have 3 members, 59, 71, and 2. Okay, then we have 59, 71, and 2. Now, for the data value 2, it is located in row 3, column 0. Okay, we don't have anything in row 2. Okay, for row 2 it is all 0. Okay, then we don't have that empty circular list, okay, in the orthogonal list structure. Now, all the header nodes, okay, in the structure are also connected, okay, as a vertical circular linked list using the down pointer. Okay. You will see that when we connect all the header nodes of the row and column together, we also have a header for the header nodes. Okay, now this node, okay, is the overall header for the two-dimensional list structure. And in the row and column data field, we will store the actual dimension of the sparse matrix. Okay, now you see that in this example, the dimension of the sparse matrix is 4 by 4. Okay, so we store the actual dimension of the sparse matrix in the overall header. Then in the program, we will maintain one pointer variable that is used to point to this header node. Okay, so every time when we access this orthogonal list structure, it will be through this external reference. Now we have the graphical structures of the data structures. Okay, so every time when we have a representation, we need to decide our programs to manipulate the data structures. Here I show you a simple example. Okay, the simple get function. So if you want to find out the value of the data at the index I and j, okay, that is the row index is I, the column index is j. Now when we write this matrix square bracket ij, so it is the hypothetical two-dimensional matrix. Okay, this is the concept that we are trying to model. But in the physical representation, the matrix is represented by the orthogonal list. Okay, so if you want to find out the value, okay, of the data at the row index I, column index j, okay, so we have this get value function to return the value of this data member. Now to find out its value, okay, we need a reference to the orthogonal list, the variable m. Now to traverse, to find out the value of the element, first we will find the given row, row I, will it exist in the orthogonal list? Meaning that is there will be any non-zero data value on row I. So we will do a search, using a pointer variable p. P starts from the member, the node below m. So now this is the pointer m. This is node m. P will start from this node. And when you write a loop to process a circular list, the termination condition will not be testing if the pointer is null. Okay, so you will not say that while P is not null, then you continue with your loop. Because when you traverse the circular list, the pointer P will never, be assigned a null value. Okay, so you will terminate the loop when the pointer come back to, the header. Okay, it means that you have made one full round of inspection, then you stop. Okay, so the control will be as long as P is not equals to M, so you have not come back to the header. Okay, and so far you have not found the row, the given row, then you repeat. Okay, now within the loop, you compare the row number of the horizontal header node. If it is less than I, you continue the traversal. Okay, you go to inspect the next row. Now if it is equals to I, then you have found it. Okay, then you have found the row. Otherwise, if the row number is greater than I, then you don't need to continue the search. Okay, because all the remaining rows will have the row index greater than I. Okay, so you don't need to search further. So to terminate the loop, you can assign the value M to P, such that when they come back to the while statement, this test will terminate the while loop. Now when the loop is terminated, you make a decision based on the value of found row. Okay, whether you have found that row. Okay, if you don't find it, you don't need to do any further computation. You simply return 0, because if you don't have this element in the orthogonal list, then it means that its value is 0. Okay. Now, if you find a row, then you need to search for the column. Okay, now to search for the column, we use the pointer variable Q. Okay, now if you find a row, for example, you find a row, and you need to inspect, the data node in the horizontal linked list. Then you use the pointer Q. That starts from the right member of the header. So you follow the right pointer, you start the search here. And once again, your loop condition is as long as you have not come back to the header, then you will continue the comparison. If the column number is less than J, you move to the right. If the column number of Q is equal to J, then you have found it. The value of that member will be equals to the value stored in the node. Now otherwise you stop. So to stop this while loop, then you can set Q to P. Then you terminate this in a while loop. Now this example is to just to let you have some general idea that the application of linked list is not restricted to what you have done in today's exercise as a linear linked list. Now when I was a student, when the teacher teach about linked list. All the exercise and exam questions will not be on the simple linear linked list. It's too simple. And the teachers typically go through it, cover it in 15 minutes, that's all. Okay, and all the programs we are going to do are two-dimensional linked list. Okay, but these days, okay, we don't do anything, any exercise on multi-dimensional linked list. Okay. Students find it too difficult. And this is the reality in today's. Okay. Now, before we move on, okay, I don't have the material here, so I don't mention it. Okay. So we will not go further, okay, about the applications of multi-dimensional lists. Now, in the remaining part of the notes on linked lists, okay, it is about the implementation of linked list as a class in the C++ language. Okay, so all the concerns, okay, related to this part are similar to what we have talked about in the examples on the array-based list. Okay, so basically, when you design, implement a class, and that the object instance of that class involves some dynamically allocated memory resource, then you need to redefine the assignment operator, the copy constructor, and the destructor, and so on. Okay. But I think I don't want to get into the detailed discussions, okay, of this part of the materials, okay, this time. I will leave it to you. Okay, if you are interested, you will go through it yourself. Okay. So in the test and exam, if there are any questions related to linked list, okay, we are only restricted to the simple linear linked list. Okay, it can be singular link, it can be circular, it can be W link. Okay. Now we will move on to discuss the next topic, okay, on stack and queue. Now before we start the discussion of the data structure stack and queue, okay, I would like to introduce the term abstract data type to you. Now, abstract data type, why we are interested in this aspect, and why we say that something is abstract. Okay. Now, in algorithm design, okay, very often we want to specify the solutions for solving a problem without concerning too much about the lower level implementation details of the supporting data structures. Okay. So that's why we want to define, okay, the behavior of certain data structures without concerning its internal implementations. And this would allow us to focus more on how to design the algorithms for the higher level application. Okay. So the term abstractions, okay, in computer science, it means that we would like to, okay, focus our attentions to the most important concept, okay, of the problem without, okay, worrying about the lower level implementation details. Okay, so this is the general idea. Now, to define an abstract data type, okay, basically you need to provide three things, three components. The first thing, of course, is the name of that abstract data type. And within the data structures, okay, it can hold certain values. Okay, then you need to define what are the domains of the values. Okay, meaning that what you can store into that, okay, data type. And then you will have a set of operations, okay, that can be applied to any object instance of that data structures. Okay, and you specify what will be the behavior, okay, how different operations behave. Now, having known these three, okay, things, okay, of an abstract data types, then you can use it in your in the design of the algorithm to solve a higher level application. You don't need to worry about the internal implementation details of the abstract data types. And the other programmer can take up the jobs to actually implement the abstract data type. So you can have a sharing of the workload. So you decompose the system, okay, into several parts. Someone is responsible for implementation of certain parts, and someone will keep on using that to solve other parts of the problems. Now, one commonly used abstract data type data structure is the stack. Okay. Now, a stack is a list of homogeneous elements. Okay, where when you do the insertion and deletion, it will be carried out at the same end of the list. Okay, and sometimes a stack is called a last in, first out data structure. Okay, so the last thing you put into the data structure is the first one that you take it out. Okay, so it is last in, first out. Now, the operation that one may like to apply to a stack includes the following. Okay, you initialize the stack to the empty state. Okay, so after initialization, the stack is empty. You test whether or not, okay, the stack is empty or not empty. The top function will retrieve the value of the top element and return that value to you. Okay. The push function is used to insert an element to the stack, and the insertion is done at the top of the stack. Now the pop function will remove the top element. Okay. And the size function will tell you how many elements are there in the stack. But one remark here is that the size function is in general not required in most applications that involve the stack. In most of the case, we don't concern about the overall size of the stack. We only concern about if the stack is empty or not. Okay, if it's not empty, then we can perform certain operations. If it's empty, it may be the case that the algorithm will terminate, and so on. Okay. Now, in the C++ standard template library, STL, we have the implementation of the abstract data type stack. Okay, so we have a class stack. Okay. Now, in the STL library, the following functions are defined. Okay, and in this part of the notes, I would try to follow the notation, of the C++ STL library. Now, when you are defining an abstract class, because we only define the external behavior of the data structure, we don't really provide the implementation in this, up to this moment. So all the functions are defined to be pure virtual function. That means that we don't give an implementation. Now the syntax to define a function to be a pure virtual function is that after the declarations of the function, you have this assign 0. So it's a syntax used in the language to denote that this function is a pure virtual function with no implementation provided in this class. Now there's one remark about this initialize function. This function is not part of the C++ STL because in general the initializations will be taken care by the constructor of the class. Because when you use the constructor to create an object instance, then by default it will be the stack will be initialized to a given state, that is the empty state. So you don't need that explicit initialization function. Now the function empty return a Boolean value, true or false. Now the function top returns the top element. In the STL, the top element is defined to be returned by reference, not by value. And when it returns something by reference, we say that the value is a L value. I will explain to you what is L value in a moment. Now when you push an item onto the stack, there are two versions of the push function. The first one is to push an item, and this item is passed by reference. That is something that you have seen in many of the exercises or some of the example codes. We pass a structure or objects by reference. And we call this item is a L value. And one single ampersand means that the item is a L value. Now the other version of the push is to push an item, but this item is a R value. And this item is passed by reference, not by value, to distinguish the two different cases. The syntax is a double ampersand. Then it denotes that this item is a out value. Now for the pop function, it simply removes the top element, but it does not return anything. It just removes it. It will not return the value of the top element. If you want to get the value of the top element, you call the top function, and then you call top. Then you get the value and then you remove it in 2 steps. But in most other languages, like Java, the pop function will return the top element that has been removed. So there's a slight difference from the C++ implementation. We may keep it in mind. Now, let me talk about a few other things and I will explain to you what is the R value and L value. Now in the textbook, there's also a function called full to test if the stack is full. Now this function full is not part of the STL. The reason is if the stack is implemented using a linked list, then conceptually it is never full because the list can always be extended as long as you have memory resource in the system. So if you run out of memory resource, then very likely that your program crashes. So the full function is not part of the STL, so I don't include it in our examples for the abstract data type stack. Now, the top function returns the top element by reference instead of by value. Now in the textbook it uses the version, the definition of the top function is returned by value, but in the STL it is by reference, so I don't include that option. Okay, returning the top element by value. Now, when you return the top element by reference, then the user of this function can actually modify the top element because you get the reference of the top element. Okay. Now, actually in the STL, there's another version of the top function that returns the top element by reference, but it is a constant reference, meaning that you get the value of the top element, but if you are using this version, you will not be able to modify the top element through the return reference. Now that's the difference. However, for the user who is using the top function, I just write my code stack.top. I don't specify which version. Okay, it is either the first one or the second one. Now, don't worry, the compiler will find out for you. Okay, so if you call the top function and the return value is assigned to a constant reference, then the compiler will use the second version. If you assign the return value to another reference variable and then later on you modify the value, then the compiler will use the first version. Okay, so the user don't need to specify which version you are using. The compiler will resolve it for you. Now, let's get to the discussion of what is L value, what is R value. When you have an assignment operator, okay, you do an assignment. Okay. In the assignment statement, what is allowed to appear on the left-hand side is called a L value. And what can appear on the right-hand side of the assignment statement can be a L value or a R value. Okay, so a R value can only appear on the right-hand side of an assignment. An R value cannot be put on the left-hand side of the assignment. Now, let's say some simple example. Okay, we define a variable I. Okay, so I, the symbol I, represents a permanent memory location in your program. Okay, so when I exists, it is mapped to a memory location. Okay, so this is a L value. Then you can put it on the left-hand side. You assign some results. Okay, the result of some computation to this variable. Okay, so I is a L value. 2 plus 3. Okay, 2 is a constant, 3 is a constant. Okay, so 2 plus 3 is an intermediate value produced by the ALU. Okay, so this intermediate result is a R value that it can only appear on the right-hand side of an assignment. You cannot write a statement that 2 plus 3 assigned I. This will be error. Okay? You cannot write something like this. Okay, because 2 plus 3 is a R value. Now here are some more examples. So we define the variable J. J assign the value 2, no problem. Okay, because J, a variable, is a L value. Okay, the constant 2 is a R value, so the statement is correct. But you cannot write the other way. say you assign j to 3, then it's an error because the constant 3 is a R value. It cannot be placed on the left-hand side of the assignment. Now, if you have defined a function, you define this function to return the result by value. Okay, then the returned value is a R value because you receive and return value. That return value is an intermediate entity. Okay, that item is returned by value. Okay, so this item is only exists intermediately. Okay, so once the return statement complete, that item disappears. Okay, so it's an R value. So in this case, you can write your statement like you return the return value of these functions to J. It's okay because the return value of the function call is a R value. But you cannot write the other way around. You cannot say I assign the value 3 to the return value of foo bar. You cannot do so because the return value of foo bar is a R value. Okay? And you cannot say I obtain the address of the return value of foo bar. Okay, because foo bar, the return value of foo bar is a R value, so it's not a permanent entity. Once the return finish, that object disappear. Okay, so you cannot get the address of some intermediate entity that will disappear right after the function return. Okay. Now, how about L values? Okay. Now the first case is simple. Okay, I don't repeat it. Now, if you define a pointer, you can use the address of operators, apply it to a L value. Okay, now you get the address of a L value. Now an L value means some objects that have a it will exist after the execution of that statement. Okay, so its address. Okay, that object remains exist after this operator. Okay, so we get the address of the variable I, put it into P1. Okay. Now, you can also define a reference variable that refers to a L value. Okay. Now, if you define a function that returns the result by reference, then it means that this function must return a L value by reference. It cannot return a R value by reference because the R value disappears after the return. Okay? Now, if it returns a L value by reference, then it is legitimate to do something like this. You assign a value to the return value of that function. Okay, so far you may not have written statement like this. Okay, but later you will start to use this kind of operations. If you are puzzled about this, statement, let's see a more concrete example. Here, a function is defined. Okay, that function receives an array of integers and an index k. Okay, it will do some steps and then it returns a result by reference. Okay, now it simply returns this k by reference. Now, the return value is by reference. Okay? Then in the other parts of the function programs, you may have a statement like this. Now, suppose the array A originally has the content 1, 2, 3, 4, 5. Okay? Then you call the function with a k. K is 4. Okay, so it means that this function will return a4, that is, okay, the value 5 by reference. So returning this value by reference is actually, it is returning the memory location storing the value 5, right? Okay, so it is returning the memory location that stores the value 5, and you assign the value 6 to that location. So after the execution of this function call, the last element of A is changed to 6. Now coming back to the declaration of the function top. Okay, when the function top returns the top element by reference, then in the usage of the stack, the programmer can replace the top element in the stack by calling the top function and put it on the left-hand side of an assignment statement. Okay, so without these features, if you want to replace the top element, then you need to pop the top element and then put in the new one. So you need to do it in 2 steps. But if the top function returns the top element by reference, then you can do it in 1 step. Okay? Now, so far about this R value and L value. Okay, now let's get back to this R value reference in a function call. Now, when we use the stack, okay, now the stack is defined in the C++ STL. So if you want to use it in your own program, you will have this include statement. Okay, at the top of your program. Now suppose we have a function, okay, that computes the greatest common divisor of 2 input values, m and n, and the returned value is a R value. Okay, meaning that after the return, okay, after it returns the value n, okay, the storage of the variable n disappears. It is taken back by the system. Okay, it is an automatic variable. It no longer exists. Okay, so that's why the returned value is a out value. Now, if you have a stack, okay, let's say we have the variable I. When you say that s dot push I, so you push the value I onto the stack instance s. Now, s is the stack of integer. Okay, now this variable s is a stack of integer. Okay. When you're calling this push function, you provide a L value in the parameter. Then the compiler will use this version of the push. Okay, so you are pushing a L value by reference. Okay. Now, it's very often that, okay, if we have a stack of integer, we have some other computations, and the result is produced by some function. Okay, let's say GCD. Okay, we call the function GCD to find out the greatest common divisor between I and j, and then we push that return value onto the stack. Okay. Now, when you are calling this push statement, you are providing a R value, okay, which is a return value of the function GCD. then the compiler will use the version of the push that receive a R value by reference. Okay. If you don't have this function, then this statement will be illegal because the compiler cannot change that R value into a L value reference. Now you may wonder why we did this. Why don't we just define that a push function receive the parameters by value? Why it is all the times must be by reference? The point is, in general, okay, when you are using a stack, in some applications, you are pushing some data object onto the stack, and that data object can be a large object. So if you are passing the parameter by values, then this will incur a lot of extra effort to do the copying of the data in the function call. So it is very inefficient. So if you pass an object by reference, the system only need to get the implicit address of that object. Now, when you have an intermediate results produced, and you want to pass that by reference, then it means that you cannot do it as usual. The compiler needs to apply certain tricks, such that some R value can be passed by reference without the need to do the time-consuming data copying. So the compiler needs to use certain tricks in generating the machine code, such that when the GCD function make a return, don't destroy that intermediate data right away. Keep it in some places and then pass that by reference. So this features, the R value reference, was introduced to the language in 2011. Now, let's see the top function. When we have the stack, the first push, the first statement, push I. After the first push, we have the value 10, in the stack. And the top element in the stack is, the value 10. Now the second push, we are pushing the return value of the GCD function, and the GCD function returns the value 5. The greatest common divisor between 10 and 25 is 5. So after the second push function, now we have the value 5 sitting on top of the value 10 in the stack. Now we have two objects in the stack. So when you say s dot top, s dot top will return this element by reference. And when you say that the top element, I receive it, I perform an operation on it and then put it back to the top element. If I do a subtraction, of the top element, I subtract 2 from the top element, then the top element will change it to 3. So when we execute these steps, the top element will be changed.